In lecture 28, we finished talking about optical transitions, focusing on the Beer-Lambert law and how the direct and indirect bandgap semiconductors will have different absorption spectra. And then we started talking about semiconductor devices. We introduced different kinds of electronic and optoelectronic devices, and then started talking about the equilibrium band diagram of metal semiconductor contacts. The details of the metal semiconductor contact will be left to the next lecture. The first student learning outcome is that you should be able to use the Beer-Lambert law to predict intensity attenuation as a light wave is propagating through a medium. So as a light wave is propagating inside a medium, some of the photons may be absorbed, and so the probability of those photons being absorbed will depend on these material properties. So if we look at the flux or the intensity of the light wave, the reduction as it propagates forward by a certain distance will depend on how many photons you have in the original intensity, and also the distance it propagates forward. That gives you a different kind of probabilities. Okay? So the proportionality constant alpha is the so-called absorption coefficient. It has a unit of 1 over length, and this 1 over length. So typically use an inverse centimeter, but this absorption coefficient really determines how the light intensity will change as the wave propagates forward. So if you follow this change, you can get the actual dependence is so-called Beer-Lambert law. The intensity actually will decay exponentially with a decay constant of alpha. At the distance of 1 over alpha, the intensity will go down to 37% of the starting intensity. That means 63% of the intensity has been attenuated or has been absorbed. When you double that propagation distance, the intensity will further decay to 13.5% of the starting intensity. This 1 over alpha is a characteristic length for the optical absorption, and we also call that absorption length. So the second student learning outcome is that you should be able to explain the difference in the absorption spectrum of a direct and indirect bandgap semiconductor. So the absorption coefficient typically is wavelength dependent. Showing here are the so-called absorption spectra of gallium arsenide and silicon, two different semiconductors. The absorption coefficient is proportional to the abundance of the initial states, which are in the valence band, and the final states, which are in the conductor. So when you pair up those states, anytime you have the distance energy difference match up with photon energy, you have absorption. So on the absorption spectrum, there are a few characteristic features. One is the cutoff or the onset of absorption, depending on which way you're looking at, which direction you are looking at. So that absorption onset or the wavelength cutoff really is related to the band gap of the semiconductor. Okay, so you have a minimum frequency or maximum wavelength for the light wave that can be absorbed by. And in general, as you go up in photon energy or go down in wavelength, the absorption coefficient will increase. That indicates that there are more and more electronic states that can participate in this absorption process. You can get to the 5th inverse centimeter for the absorption coefficient at high photon energy. And just above the band gap, now we are actually seeing a different behavior. As you see for gallium arsenide, the rise in the absorption coefficient is very rapid when you just go above the band gap. But for silicon, it goes up much more slowly. Eventually, it'll go up rapidly as well. So this behavior actually is related to the band gap types of these materials. In a direct bandgap semiconductor, like in gallium arsenide, as we explained in last lecture, only a photon is needed to induce the transition from up to bottom. So that transition can actually happen at a very high rate. So that's why, as soon as you have a significant amount of states providing that transition, the corresponding absorption coefficient will rise up dramatically. So that's what we have seen in gallium arsenide or indium phosphide or in this like a quaternary material. But when we go to silicon or germanium, those are the indirect bandgap semiconductors. As we explained earlier, to induce the electron transition from the top of the valence band to the bottom of the band, we do need a third particle, phonon, to be involved. And that extra particle involved in the process will slow down this transition, and that gives you a relatively slow rate. So that's why even though the absorption can still happen, the corresponding absorption coefficient will be lower than what you have in gallium arsenide with the same energy difference away from the band gap. So, but this also means that if you have a phonon involved, phonon does have a little bit of energy. So in general, the minimum photon energy that can induce this transition in the indirect band gap semiconductor could be just slightly below the band gap, very small, tens of millieVs. The last student learning outcome is regarding the semiconductor devices. Since we didn't go very far, here I'm only requiring to present 4 different types of basic building blocks that have been commonly used in semiconductor devices. These are the 4 different kinds. One is the metal semiconductor contact, and then the other one is the second one is the semiconductor pin junction, type silicon. Then if the semiconductors are different, let's say you have silicon on germanium, or you have gallium arsenide on aluminum arsenide, now you have so-called semiconductor heterojunctions. Finally, you can also involve oxides, or we can have a metal oxide semiconductor structure or MOS structure. Sometimes you see a mix, the ion being isolated in the middle. Those are the structures commonly used in many of these transistor devices in electronic systems. This is the end of the review.